Alright, welcome back, physics. Today we are going to be talking about interference and harmonics. You're going to have two homework sets over both, and that'll be it for this week. So let's get started. And let's pull up the pointer here. Alright, so interference of waves. You should have experimented with this a little bit in the simulation, or if you actually did it in person with a Slinky. So when we have interference, notice that both of these wave fronts, or both of these wave pulses, have an amplitude of 1 box. So when they interfere with one another, right, when they collide, they're going to have now 2 boxes of amplitude. If they're on opposite sides, one has a positive amplitude, another has a negative amplitude, then when they interfere, we have an amplitude of 0. If I had 1 box and 2 boxes, we would have an interference that would get them up to 3. If this was 2 boxes high and 1 box high, then we would have an interference that would bring them back to 1. So interference is what we call additive, right? I add these two together, gets me 2. These two, I add them together. Since this one is a negative amplitude, they subtract, and I get 0, okay? So this is all interference of waves is. And when you're dealing with music, dissonance is really bad interference. When you have harmony, they add together. So you are getting a nice wave shape versus an ugly wave shape that is all over the place. All right. So that's all you really need to know on interference, is that they add together. The next thing is what we call standing waves. If you have ever used a jump rope or you've seen a jump rope, you have seen a standing wave. A standing wave is just when the wave goes up and goes down, and it really doesn't look like it's traveling across the medium. So for a standing wave, here you'll see that we have a solid line and a dotted line. And this is because this bump here, this crest, is going to become a trough, and when this is a trough, this part of the wave becomes a crest. So it just goes back and forth and back and forth. It really doesn't look like it's traveling across the medium. Okay, so there's 2 more words that you need to know for this unit. One is called a node. The nodes don't look like they're moving at all. They look like they stay in the same spot, whereas the antinode, that's the part that becomes the crest and the trough. So if I mention a standing wave, that means that the wave is not traveling across the medium, or it doesn't look like it's traveling across the medium, sorry. And it's only looking like it's oscillating in place. Notice as well, we have this wavelength, right? It goes up to the antinode, down to the node, down to the antinode, and then back to a node, right? It's got to go there and back to where it started. So harmonics, if you think back to the intro to Waves Lab, we made some standing waves, and what I ask you, what do they look like? How many bumps in the Slinky were you able to create? Right? I had you put 1, 2, and 3 bumps in the wave, and it should have just looked like it was going up and down, right? So these standing waves we call harmonics. So each time we add an antinode, we achieve what's called the next harmonic. So the first harmonic looks like this. This was the first part of the standing waves portion. So how many wavelengths occur in this first harmonic? That's my question to you. If we go back to our picture here, you'll see that we only have 1 bump in our picture. So that means that we have half of a wavelength, right? We have 1 antinode, we have 2 nodes, right, at the ends that it's being held. If we go to the next one, what about the second harmonic? How many wavelengths are there? Well, now we can go up, down to the bottom, and back here. So we have 1 full wavelength. If we go to the third harmonic, now we have 3 bumps, right? We can go up to the top, down to the bottom, back up to the top, and to another node. So now we have 3 bumps. We have 3 halves of a wavelength. So every time we add in a harmonic, every time we add in an antinode, we get 1 more half of a wavelength. So what we can do is we can figure out a rule for harmonics. So normally I would have you work with shoulder partners, but I would like you to create your own rule for harmonics before you move on with the rest of the video. So take a moment, think of how you could relate the harmonic number, right? We have the first harmonic, second harmonic, and third harmonic, and I want you to relate that to the wavelength. So come up with some equation that you could multiply the harmonic number by to get the number of wavelengths. So pause the video, take some time, figure out what this is. All right. So what you should have found is something that looks like this. So if you have the length of, if you have the length of your string, the harmonic number divided by 2 multiplied by the wavelength should get you that length. Or if you want to find the wavelength, the number of wavelengths, you do 2 divided by n multiplied by L, and that will give you the wavelength. Okay? And here in this equation, this is the n, capital N, is equal to the harmonic number. Okay? So now that you know some things about interference and harmonics, you can answer the questions on those 2 homework sets. Okay? Also attached to this material are the physics classroom links, and you can read through those if you need a little bit more help. All right, I'll see you next time, physics.